Hello everybody, welcome back to another Gregorius Maths video. In this video, I'm going to be... I'm out of breath from doing the intro, I haven't done it in so long. Anyway, I'm going to be introducing... Actually no, I'm sorry. I'm going to be continuing the homological algebra series after a little while. And in this video we're going to be introducing the Rham cohomology. So, in the last video in this series, we talked about chain complexes, so we generalized the notion of a chain complex and how you define cohomology in general. And so now we're going to use cohomology and the new technology that we have, homological technology that we have, in order to, I'm quoting Tao here, measure the extent to which the fundamental theorem of calculus is fails on higher dimensions and on manifolds in general. So, okay, we're going to need some tools. So we can't just use chain complexes here, we have to know what exactly we're working with. And the main tools that we're going to be using are differential forms. So, okay, let's get into defining what they are. So, firstly, we're working with, in the setting of Grassmann, I do German, Grassmann algebras, and basically, if dx is a very small quantity, then dx squared is basically 0. So the Grassmann algebra, G star of Rn, is the algebra over the real numbers, which is generated by dx1 up until dxn, subject to the relations that dxi all squared is equal to 0, and dxi all squared is equal, all squared is equal to 0, and dxi dxj is equal to negative dxj dxi. And and this is graded, so this algebra here is graded, which means that it's the sum over p, or over the integers p of gp Rn, where g0 of Rn is just equal to the real numbers, and gp is the vector space generated by dx1 up until dxp. And also note that because of this relation here, we have that gk of Rn is equal to 0 when k is bigger than n. And that's because it would force one of these dx's to repeat itself, and that would make the whole thing equal to 0. So, okay, now we want to define functions here. And to do that, we'll use differential forms. So the set of differential forms is, what you do is, so we'll denote it by omega p, Rn, and this is just the set of all C infinity functions on Rn. So what does that mean? That means the set of all functions which has infinitely many derivatives, and then you tensor it with this Grassmannian algebra. So the pth one, so that means generated by dx1 up until dxp. So that's what a p-form is. But okay, let's write this more explicitly. So if we say it's equal to omega, then this would be a sum over I of fi times dx I, where I ranges from I1 up until IP, and all of these functions are C infinity functions on Rn. So, for example, let's have a look at what this looks like. So, if we wanted to define a two-form, so an element of omega 2 R3, an element of this would look like f1 dx dy. So here the two form part means it's got two of these dx's. So we have a C infinity function on R3 dx dy plus f2 d, what do I have here? What do I have written here? Yeah, dx dz plus f3 dy dz. And those are all the combinations that are not zero. So this is what a two form on R3 would look like, where again all of these are C infinity functions on R3. So with this in mind, we want to see how this actually relates to calculus, because so far, okay, we have dx's and dy's and stuff, but where's like the differentiation? Where's the integration? Okay, we won't go into integration in this video, but differentiation we'll go into right now. And this is given by the exterior derivative. So the exterior derivative takes in a p form and it gives you a p plus 1 form. So the exterior derivative, we'll call it dp, which goes from omega p Rn to omega p Rn plus 1, is given by the following. So d0, because note that a zero form is just a function. So d0 of sum f is equal to the sum over I of the partial derivative of f with respect to all of the coordinates, and then dxi. And then, so this here becomes a one form because it would just be the partial derivative of f with respect to x, dx, plus the partial derivative of f with respect to y, dy, and so on and so forth. So it's just the sum of a bunch of, it's just a one form, basically. And then dp of f, so if we're given, actually I'll say dp of omega. So if omega is a sum as we were given before, like this, then dp of omega would just be d0 fi times by dxi, like so. So it turns this into a one form, and then this omega, this p form omega, becomes a p plus 1 form. And the important part here, considering this is a homological algebra series, the important part here is that dp composed with dp plus 1, sorry, dp minus 1 is equal to 0. And of course this means that we are setting up a chain complex here. So, before I get into that chain complex, I'd like to give an example of how this exterior derivative actually works. And it's quite an illuminating one. So, the exterior derivative is basically the ultimate generalization of the derivative. So, if we have So when we look at R3, so 3D, if we have some f, some function f of x, y, z, then d0 of f is equal to, well, we take the partial derivative with respect to x, dx, plus the partial derivative with respect to y, dy, plus the partial derivative of f with respect to z, dz. Now, if we have some one forms, so what would a one form look like? Well, if we had some one form f1 dx plus f2 dy plus f3 dz, and we took, I'm going to change the pen to something that works better. So if we did d1, if we call this omega, if we did d1 of omega, what would we get? Well, okay, this is a little bit more complicated now. So, firstly, with respect to x, what do we have? We have to take d0 of f1. So, we're going to get the partial derivative with respect to f1 of, the partial derivative with respect to f of f1 plus the partial derivative of f1 with respect to y plus the partial derivative of f1 with respect to z, and then we're going to have to do that, and don't forget dx, the dy, dz, and then all of that, because of this, we times it by dx. And then we have to do the same thing for f2 and f3. So we have the partial derivative of f2 with respect to x plus the partial derivative of f2 with respect to y plus the partial derivative of f2 with respect to z, dx, dy, dz, and this time we times it by dy. And then we add the partial derivative of f3 with respect to x, dx, plus the partial derivative of f3 with respect to y, dy, plus the partial derivative of f3 with respect to z, and then we times that all by dz. And if we use the fact that, well, if we have to use these relations here. So anytime we see two dx's next to each other, that's 0. And also, we don't want to write dy dx. We would rather write negative dx dy, just because it's nicer that way. And so if we keep this in mind, what we end up getting is, once we expand everything, what we end up getting is the partial derivative of f3 with respect to y minus the partial derivative of f2 with respect to z, dy dz, minus partial derivative of f1 with respect to z, minus the partial derivative of f3 with respect to z, dx dz, plus the partial derivative of f2 with respect to x, minus the partial derivative of f1 with respect to y, dx dy. If you expand it, you should get that, hopefully. And for a 2 form, I sort of want to write this all on the same page. Oh, well, never mind. Can't always get what you want in life. Hey ho, the wind and the rain, eh? So if we have a 2 form, f1 dx dy plus f2 d minus, putting a minus sign here, dx dz plus f3 dy dz, then d2 of omega is going to end up giving you partial derivative of f1 with respect to x plus the partial derivative of f2 with respect to y plus the partial derivative of f3 with respect to z, dx dy dz. Now, if we go back and look at what we have here, this d0 is precisely the gradient from vector calculus. This d1, which we ended up with here, is precisely the curl. And this right here is precisely divergence from vector calculus. So hopefully this example sort of shows how the exterior derivative is really like the ultimate generalization of the derivative, basically. Now, with that out of the way, with some motivation, some understanding of what we're dealing with now, let's go back to this relation here. So, obviously, we look at that, we're in the middle of a homological algebra series, a chain complex is getting set up. So, let's set up the, let's not dilly-dally now, let's not be silly, let's just define it. So, also note that everything that we've done so far, so if I instead said U instead of Rn, where U is some open subset of Rn, everything that we've done would still work. So we're going to define de Rham cohomology for any open subset of Rn. Okay, so the de Rham complex is the sequence. So we have 0 forms, we have 1 forms, and so on, up until n forms on U, sorry. And then we get back to 0 because anything above an n form in Rn is going to be 0. Remember, U is just some open subset of Rn. And what are the maps in between? Well, if it wasn't the exterior derivative, then what the hell am I doing? So, yeah, it's the exterior derivative, so we get d0, d1, up until dn minus 1, and so on. And of course, if you've watched the previous videos, you'll already know that the de Rham cohomology, the Pth de Rham cohomology, is of U, is equal to the kernel of dp mod the image of dp minus 1. Yeah, okay. So, and elements of the kernel are called closed. Yeah. Elements of the kernel are called closed p-forms, and elements of the image are called exact p-forms. That's just a bit of notation, terminology for you. But okay, so now we've defined this, let's take a look at an example. And the first example is the fundamental theorem of calculus, basically. The fundamental theorem of calculus says that the first de Rham cohomology of the real numbers is equal to 0. Okay, well, no, but this is true because of the fundamental theorem of calculus. So let's see why. Well, let's investigate this. So, okay, we're taking the kernel, but the kernel is going to be the whole of this thing, because, well, anything above a 1 form on the real numbers is just going to be 0. So, what we really have to show is that every single we have to show that every single 1 form, g over x dx, is in the image of d0. So that means it's equal to d0 of f for some f. But because of the fundamental theorem of calculus, we already know what f is. So every 1 form, g of x dx, is of the form d0 of f. So if we say that f of x is equal to the integral from 0 to x of g of x dx, then sorry, excuse me, then the derivative of f of x is equal to g of x by the fundamental theorem of calculus. And therefore d0 of f is equal to g of x dx. And therefore every single one form in here is in the image of d0 because we just define f as this integral here. F of x is the integral from 0 to x of g of x dx. And so there's no obstructions to the fundamental theorem of calculus. And so the image, so the kernel of d1 is equal to all of the one forms, but then also we have the image of d0 is all of the one forms. And so when we do that mod that, we just get 0. So let's have a little breather here to interpret what we've actually done. Well, the fact that this is true, well, listen, cohomology, in fact, all quotient groups in general, but cohomology is an excellent way of seeing what the obstruction, or how many obstructions there are to something that you want. So we want the fundamental theorem of calculus to be true, let's say. And so with the de Rham cohomology here, we see that because this is 0, there are no obstructions. So for functions on R, so that take one variable, over integrated over this integrated over, how do I say this, over a line interval, so from A to B, the fundamental theorem of calculus holds. But of course that's, well, as we're going to see, that's not always the case. So an easy example of this is to say that the 0th cohomology of U, where U is some subset of Rn which has m different components, then this is just going to be Rm because, well, the kernel of the derivative function basically would just be, well, obviously the kernel of the derivative is just constant functions, but because this is split into m different components, then it could just be like the first component is there, then the second component's like this, and the derivative of that function would still be 0. And so, yeah, that's like a quick example of something that sort of shows how what we assume to be true about calculus isn't always true. So we would say if the derivative of a function is 0, then it's constant. But in this example, it's not just constant. It's not constant because, well, it has different values depending on which component of U you're in, but still the derivative is always 0. So basically what I'm trying to say is when you do calculus on the spaces that aren't, the real numbers, things can act weirdly. Now, speaking of doing calculus on spaces that aren't the real numbers, let's generalize this to manifolds. So, manifolds are spaces that look like Rn when you zoom in, basically. So, let's get a little bit more specific. An n manifold M in R capital N. So it doesn't have to be in Rn, it could be in some space which is more than n-dimensional. For example, the circle would be a 1 manifold even though it's in R2. So an n manifold in Rn is a Hausdorff space M. Is a It's a Hausdorff space such that, and here's the important part, for any x in M, we can find a neighborhood U sub x of M such that there is a homeomorphism phi x from ux to Rn. And this pair of neighborhood and function ux phi x is called a chart. So, okay, yeah, so basically what we're saying is, and this definition makes perfect sense because when we zoom into a point x, or the area around that point x, we can find a homeomorphism between that and Rn. That's sort of what it means to look like Rn. So, now another thing we need to define is an atlas. So, an atlas is just a family ui phi I such that of charts such that ui covers is an open cover of the manifold M. So when you take the union of all of these neighborhoods, you get the manifold M. So now we know what a manifold is, and the fact that it looks, okay, so it looks locally like the real numbers. So locally, we should be able to do calculus on a manifold without many issues. But how do we take this local information and make it global? So we want to define differential forms, not just locally on these neighborhoods, but for the whole manifold. So here's what we do. So firstly, so firstly note that any manifold M can be parametrized by embeddings psi. So if we have psi I from ui into Rn, where these neighborhoods, sorry about that guys, the camera just fell down, tripod's sort of broken, but that's okay, where the neighborhoods ui, Rn are little n, and these parameterizations are basically giving that neighborhood local coordinates, basically. And when we take the union of all of these parameterizations, we get the manifold itself. So the union of psi I of ui is equal to manifold. Okay, so with these parameterizations in mind, we can try and see if we can globally do calculus. So, okay, let's just dive right in. So, if we have some let's start off, before we go into differential forms, let's just start off with a function f from M into the real numbers. So it takes some x. Remember, this is just, these elements of the manifold are coordinates, are given by some coordinates like this. So it would assign to some element of the manifold x a real number r. And we want to ask, is this function differentiable? Well, okay. Let's take this from asking such a big question to asking a more local question. So instead we'll define fi, and we'll go from fi, we'll go from just the neighbourhood into the real numbers, and all it does is it will take in these parameterized coordinates. So it will be fi of x is equal to f of psi I of x. So it takes in the locally parameterized coordinates and it spits out a number. And now, because this is just some open neighborhood, now we can freely say this is differentiable or this is not differentiable. So we'll call f ck, which means differentiable k times, if all of these local functions are ck. But we have to be careful when we're just gluing together this local information globally like that, because we have to make sure that when these parameterized coordinates, so basically what I'm trying to say is, what if there's some element that gets parameterized both by psi I and psi j? We have to make sure that our function f agrees, otherwise the whole thing collapses basically, because then it's like, well, which coordinates do you choose? Because you have two different coordinates for this point, so you want it so that this function, it doesn't matter which coordinates you pick, it still spits out the same number basically. So, more precisely, we're going to derive the change of coordinates function. So, if we have some point x, which is both psi I of some ui and psi j of some uj, then what we want is that fi of x is equal to fj of x. Now, since if we compose both sides on the left by psi I inverse, we have ui is equal to psi I inverse of psi j of uj. Then we can just swap that in here. So instead of fi of just x, what am I doing? X, yeah. Instead of just fi of x, oh, sorry. We want that fi of ui, that's what it is, that's what it is. Fi of uj, because, because we take f of x on both sides. Here we go. Then this is just fi and this is just fj. So now, since ui is just that thing that I said before, what we have is fi of psi I inverse compose psi j of uj is equal to fj of uj. And this bit here, so this is what we want, this is what we need to be true. And that composition there is the change of coordinates map. So that's the map that goes between this parameterization and that parameterization. And we want this to always be true. So, we want that to always be true. So, we just say that for all elements for all elements in psi I inverse of psi j of uj, for all elements in there, we also require that psi I inverse goes with psi j fi is equal to fj. And this is just the pullback, and it's defined as, for functions at least, in this way. It's just like that. So the pullback of fi by this composition is equal to fj for all elements of this. So this formula here gives us an idea of how to carefully go from local to global. And so we want to now generalize that onto differential forms. So a differential form alpha on a manifold M, we define alpha, a K-form alpha, is a collection of forms alpha I, which are just the pullback of alpha by psi I, which I'll define in a moment. I'll define what this pullback means for differential forms. That's the last thing I do, actually. Such that we have alpha j is equal to the pullback of alpha with respect to this change of coordinates. Alpha I, like so. So again, the idea is that when you change the coordinates, the differential form still agrees, basically. So, what is this pullback? This, sorry, I didn't even write it. Stop. This pullback. So, what it does for differential forms is, if you have some alpha equal to some gi times dy1, sorry, dyi1 up until dyi, what are we doing, k forms? Yeah, k. Then the pullback of alpha by f star of alpha. So where f is just going for some rm to rn, is given by the sum over I of gi composed with f df I1, and I'm going to define what exactly that means up until d f I k. So in order to illustrate what this actually means, I'm going to give one final example. So if we're given a two-form alpha, which is x dy dz, so it's a two-form on R3, and if we're given some function f, which goes from, say, R2, and it has to go into R3, which sends st to, what do I have written down here, s squared t cubed minus s squared t. Then the pullback of alpha by f is given by the following. So it's s squared, so it's g, so x, so f, f, which is this thing, composed with g. So all this does is it takes the x coordinate, so it's going to take s squared, so s squared d f2, f3. So what is df2 and df3? Well, that is the partial derivative of this second one. So df2 is the partial derivative of the second thing with respect to s ds plus the partial derivative of that same thing with respect to t dt, and then we times it by df3, which is the partial derivative of t with respect to s ds plus the partial derivative of t with respect to t, which dt, which is just going to give us dt. So I'm not going to bother right now, I'm just going to write dt. And this is equal to, well, the partial derivative of this thing with respect to s is, so we have s squared, and then we have negative 2s times ds, plus this thing becomes 3t squared dt, and then we times that by dt, and this is equal to, well, these two dt's are going to make 0, so we just get negative 2s cubed ds dt. So that would be the pullback. That's an example of what the pullback does. So, and in the next video, so I'm leaving it there for now. So I've defined what the de Rham cohomology is for a manifold M. And in the next video, I'm going to introduce sheaves into the picture, because sheaves are sort of a general way of taking local information and making it global. And we're going to see how to compute maybe an example or two of de Rham cohomology. So hopefully you enjoyed this video, hopefully you found it informative, and hopefully I'll be back sooner than 3 months. Alright, see you next. Goodbye.